we're only going to do 1216A here because part B is what you guys are going to do in your homework. So we need to figure out how large does the diameter of a rod need to be if it is able to experience a certain amount of torque and not exceed an allowable shear stress. And here's our setup. We have a motor over here applying 17 kilonewtons of torque, and half of that is going into rotating this thing over here, and the other half is going into rotating the second one of these things. Now, this is a pretty tough problem. We gotta divide it into steps. So our first step is to, our main goal, the first step is to figure out the diameter that this section right here of the pipe needs to be. Or I guess it's not a pipe, it's a rod. We're assuming it's a solid rod. And if we're interested in just this section of the rod from A to B, we we want to figure out the internal torque in just that section of the rod. So if we're going to find the torque in that section from A to B, we can kind of pretend we're slicing it in half. Take a section somewhere in the middle of that rod, and and we can look at all the torques acting to the left of that section. Here's our 8.5, and that's it, the only one. And we know that there must be an internal torque counteracting that, also of 8.5. And technically that's because the sum of all moments at this section equals 0. Alright, but let's look at our units. Kilonewtons times meters. And I'm going to suggest let's convert that kilonewtons times meters to newtons times millimeters. And here's why. Look at this question. In there it gives us allowable shear stress of 80 megapascal. We know that megapascal is also Newton times millimeter squared. Oops, not times, I mean per. Newton divided by millimeter squared. So we know we're going to have to make these units consistent at some point. And I'd like to go to millimeters because, well, when we get an answer, we're looking for a diameter. I'd rather have it in millimeters than meters, because I think this rod is going to be better. It's going to be small enough that its diameter is best expressed in millimeters rather than something else. So I'm going to convert kilonewtons times meters to newtons to newtons and millimeters, like this. There's 1,000 newtons and 1 kilonewton. That takes care of our kilonewtons to newtons. And then we want to go meters to millimeters. There are also 1,000 millimeters in 1 meter. So that gives us 8.5 times 10 to the 6th Newton times millimeters. Why did we want to find torque? Well, because we're using this equation again. And we're going to want to solve it for diameter. So we need to know tau max and t. And we just found the torque between sections A and B. The allowable shear stress is given as 80 megapascal. We know that's also the same as 80 newtons per millimeter squared. C is the distance from the center of the rod to the outside, which is like the radius, which is half of the diameter. And I'm going to leave that in terms of d, the diameter, because that's what we're solving for in this equation. We're also going to express the polar moment of inertia J in terms of d. So that equation for J should look familiar by now. So we're going to put all these definitions on the right into our equation on the left. And we get that. So we can make this a little simpler by canceling one d, so we know that this d to the fourth on the bottom is going to come down to d to the third. And now we just start the business of solving for d using some algebra. So the first thing I'm going to do is multiply both sides by pi d to the third over 32. And now we just have to continue solving for d using some handy algebra. And by the way, this is the diameter of the section A to B that we've been solving for. And now it's just a matter of using your calculator to get the cubed root of this. So after getting the cubed root, we're actually getting d itself for the section between A and B. And like I promised, that is in millimeters. For the second section, B to C, we can do pretty much exactly the same thing, only we have to understand that the torque is going to be a little bigger. Because when we take a section, between B and C, there are two torques on the left. They're both 8.5, they're both in the same direction. So we know the sum of all moments at this section is going to be 0. And for that to be true, the internal torque here has to counteract two 8.5s. So that torque from B to C is 2 times 8.5, which is 17. And we're going to again use the units Newton millimeters. But we have to convert it to Newton millimeters. And when we do that, we multiply by 1,000 and then 1,000 again to get that 10 to the 6th. So we don't want to forget that. So because the torque is the only thing that's different between section AB and BC, well, except also the diameter is different, obviously, that's what we're solving for. But the fact of the matter is we can set up the equation the exact same way, do the exact same math. So I'm going to bring your attention to what we came to at this point. And I'm going to rewrite that using, instead of the torque from A to B, which is right here, I'm going to use the torque from B to C, which we just found. So here's our expression for the diameter from B to C. And all I did is I rewrote that and I put 17 here instead of 8.5 because there is more torque in the section B to C. The internal torque from B to C is that entire 17 Newton meters that the motor is applying. So we take the cube root of all that and we get 102.7 millimeters. And now you guys can take it from here and do part B using those diameters we just found.
Made with Doodlecast Pro.